First of all, thank you for being here on the last talk of ICAPS 2018. So in this talk, I will present how we can compile optimal numeric planning into mixed integer linear programming. And this is a joint work with my colleagues at the University of Toronto, Margarita Castro, Professor Cire, and Professor Christopher Beck. Okay, so let's see what is the problem that we are trying to solve. We basically have an extended version of our classical temporal planning problem where we have instantaneous actions, and we have in addition, we have numeric state variables. So, for example, here we can have the load of this truck here, and of course, actions can modify the values of this numeric state variable, and we can have preconditions that account for these numeric state variables here. Okay, so we are interested in optimal numeric planning. So this means that if we have action cost, we want to minimize the total action cost of our solution. This is just a summary of the main differences between classical numeric planning, and I would like to point out that in our talk we consider a restricted version of numeric planning where conditions are restricted to be linear expression of the numeric state variables, and for the effects we consider assignment of variables to linear expression over the other state variables. Okay, this is, so in our work we are compiling this planning problem into mixed integer programming models, and there have been already work on this line here, and here I would like to mention the work, this work here with the compilation in two kind of models called state-based model and state change model. And the work in 2005 from Van der Briel, that's basically extend the state change model into the SAS+ formulation of temporal planning. Okay, so the first thing that we need to do when we want to compile a planning problem into an integer programming model is similar to what is done for SAT, is to fix the time horizon. So once we have this time horizon, we can initiate the model and solve the integer programming model until we find a solution. So since we are interested in the optimal setting, once we find a feasible solution given a time horizon, we actually need to verify that no other solutions at a larger time step have a smaller cost. So in this case, given a feasible solution, we need to verify to a time horizon that is equivalent to this expression here. Yeah. Okay. So let's talk into more details about the model that we have. First of all, we need the variables. We define a variable for every numeric state variable for every time step that we have that corresponds to the value of the numeric state variables in our planning problem. And then we have binary variable corresponding to the actions and the time step at which we are planning the actions that correspond to whatever we have this action applied to in this time step here. And okay, and for the action preconditions, as I said before, we consider only linear action preconditions and of this form here. And for action effects, we actually divide the action effects in two types of effects, and depending on the type of effect that we have, we model this effect in two different ways. So the first type of effect is what we call simple action effect, and this consists only on increasing the variable of a numeric of the state variable by a constant quantity, while the second type of effect we call it the linear action effect, and it basically corresponds to the assignment of the variable to a generic numeric expression of this form here. Okay, so now let's see in more detail the constraints. Obviously, we need initial condition and the goal conditions that are conditioned at the first and the last time step that we are considering. And then for the numeric action preconditions, so basically what we need to model is that if we want an action to be applied at one time step, the corresponding precondition has to be satisfied. So this is a logic constraint, and we can express this logic constraint into a linear constraint using the big M constraint. So these two formulations here, the constraints here, are equivalent provided that this quantity here, the M over here, is a lower bound on the expression on the left-hand side. And since we are considering fixed time horizon, it's possible to actually define pretty close upper and lower bound of the numeric variable. Okay, then if we have simple effects, basically what we want to model is something like this. So if the value of a numeric state variable at time step is given by the value of the variable at the previous time step with the addition of all the actions that are incrementing or decrementing this variable. But when we consider the action effects, we also need to consider the linear effects. So in case there is some action corresponding to when we have actions that are modifying the same variable for a linear effect, we need to basically make this change invalid. And we can do this by, again, applying a big M constraint here. So these two constraints here are saying that if we have a linear effect here, then the expression here will be satisfied anyway, provided that the M are lower and upper bound on the numeric variable, on the expressions. Okay, then if we do have a linear effect, then again, what we want to model is something like this. So if we have an action that has a linear numeric effect, we need to have a corresponding change of this type here. And again, we do it using the big M constraints. And finally, we have a set of constraints that are accounting for the interaction of actions that are modifying the same variable. So in this case, we need to make the actions not to happen at the same time. Okay, so these are the constraints that we have for the numerical part. The nice thing of this model here is that we can add these kind of constraints to any type of model for the classical part of the problem. So in our experimental evaluation for the propositional part, we take the state change model and we add these constraints here. And for the initial time horizon, we take the length of the relaxed plan that we obtain by a heuristic. In our experimental setting, we consider the optimal plan for the interval relaxation version of this problem that is presented in a paper in AAAI this year. Then we compare our compilation approach with A star with a set of admissible heuristic, and here are the results. So so we first experiment with a set of domains that feature only simple effects, and we can compare the results against the Hmax heuristic and the landmark heuristic and our optimal relax interval relaxation heuristic. And we can see that basically the compilation can actually perform pretty well. And I also wanted to point out that there are some instances in which the compilation actually solve problems that are never solved by any of the other approaches. Okay, and then we also compare with sets of problems that have both simple effects and linear effects. And in this case, we compare against the blind heuristic and an heuristic that doesn't take into account to the numerical part, because for linear effects, so far, there not been developed any kind of heuristic that directly takes into account the numerical part of the problem. And these are basically the results. So here, again, we can see that we can solve problem instances that we have never solved before with our compilation. Okay, so this is just a summary of the talk. And we are showing here that actually we can be comparable with heuristics search approach. And for future work, we can extend this formulation to other kind of planning. So for example, temporal planning, or we can consider further constraints, or like we can enrich our model in other ways. Okay, thank you. And if you have any question, I'll be happy to answer.
So are there any questions?
Thanks for the talk. On slide 15, you showed the one of the domains where your compilation solved many more problems than the middle one, the sailing domain, I think. Mm-hmm. Were you able to draw any insights from that about what is it about that domain that confused heuristic search, but was...
So actually, in this domain is very heavily like numeric. There are very strong numeric preconditions, and basically because the heuristics ignore the numerical aspect of the problem, then they're basically blind. And in our case, we can reason with numeric facts. And
maybe a similar question for the slide before this one. So did you notice any structure in domains where it didn't go so well, or where it went beyond your expectation?
Well, again, so in this graph here, we can see basically on this side here, we have domains that are, again, very numerically constrained, and these are the graphs, the problems in which we perform pretty well. And so for these other domains here, they have a strong combinatorial component. In this case, like the heuristic search performs pretty well, even though here we have a problem that we can't solve, and any of the heuristic search can solve. So,
no further questions? Okay, let's thank the speaker again.
Thank you.